Okay, thanks May, thanks Lei Ming and everyone for stimulating discussions yesterday and today. This project began a couple of years ago. It was the idea of Dan Jaffe at an AGU conference where he tried to pull together the measurement folks from high elevation sites who were measuring the three forms of atmospheric mercury along with modelers to try to push the understanding of chemistry of atmospheric mercury forward. So we have a long list of collaborators here. The objectives were to compare the available measurements with the Tekran speciated system, elemental mercury, oxidized mercury, and particulate mercury, along with ozone and meteorology from the 5 surface sites that are high elevation, and these have reported observations of dry free tropospheric air at the surface. So these observations were compared with simulated speciated mercury concentrations from the GEOS-Chem mercury model, coupled ocean atmosphere land model. And the goal was to examine spatiotemporal trends and interspecies correlations both in the observations and the model. And what we did was we looked for observations across looked for common features in the observations across the sites, tried to use the model to constrain the processes that were important for the oxidized forms of mercury. And we varied the model chemistry to probe for clues on likely oxidation mechanisms for elemental mercury. Now in this talk I'm going to be combining the GEOM, the oxidized mercury, and the particulate mercury into one measure, calling it reactive mercury, RM, due to uncertainties on what the Tekran is actually measuring, what fraction is actually oxidized or particulate. So we just combined them. There are issues with both the observations and the model, so this process was a bit iterative. We didn't assume the observations were correct, and we didn't assume the model was correct, but we decided to go ahead and do the comparison anyway. As has been talked about so far, the Tekran system, the measurements may be biased low due to poor uptake efficiency and interferences. However, these measurements may perform more accurately in extreme low humidity environments. And so that was the idea with looking at the high elevation sites that intercept dry free tropospheric air. The GEOS-Chem model has been extensively evaluated against the mercury deposition network data, as well as surface land sites, ship cruises, and flight data of elemental mercury, seawater concentrations. However, the oxidation chemistry in the model may not represent reality. As an example, what was brought up in Helen's talk yesterday from the ARCTAS flight, the vertical profile of elemental mercury in the atmosphere was not well simulated by the model. There was the lower concentrations of elemental mercury in the observations at the upper troposphere, lower stratosphere were not accurately reproduced in the model. So our approach was to filter the observations based on water vapor. We wanted to basically get rid of the outliers when we had known periods where we had upslope flow, because essentially most of these sites were at high elevation. And so if there was upslope or surface flow, the water vapor concentrations would be relatively high. And since the GEOS-Chem model represents the free troposphere, the lowest level of the model is still in the free troposphere, we wanted to eliminate the surface air contribution, the times when we had known surface air in the observations. So we created a quote-unquote free tropospheric data set of the observations for comparison with the model by selecting only times when the water vapor was in the driest 3/4. We looked at interspecies correlations of reactive mercury versus GEM, reactive mercury versus ozone, reactive mercury versus water vapor in the observations and in the model, and we compared the interspecies correlations in the observations with those in the model. The absolute observation model comparison was less important. So we weren't evaluating the model based on the observations. We wanted to determine if there were similar or different trends in both the observations or the model to get an indication of the processes that were important for reactive mercury, both sources and sinks. The 5 sites used in this study are shown by the green stars. That's what those are called. So over here we've got the Lulin Atmospheric Background Station on the island of Taiwan. And then the other 4 sites were in Western North America. We got Mount Bachelor Observatory, the Desert Research Institute, this MDN site NVO2, which is at Paradise Valley in northern Nevada, and the Storm Peak Laboratory in Colorado. And the data that was selected for these, there was about 30 days in each season from the lab site. We had about 3 years of spring and summer data from Mount Bachelor. We had about 3 years of continuous data in all seasons from Desert Research Institute. We had 1 season of summer data from NVO2 and spring and summer data from 1 year at Storm Peak. So let's just take a look at some of the data, the comparisons. I'll start with gaseous elemental mercury. So what I want to just draw your attention to the difference between the all the data and then the data that's filtered according to the water vapor. So the hashed bar here is all the data, and then the open bar is that which is filtered on the water vapor criteria. And so some of the patterns that we see across all sites in the observations are that we have the highest gaseous elemental mercury data coming from the Lulin site during the spring. You can see this bar right there. It gets up to about 2.2 nanograms per cubic meter. The lowest gaseous elemental mercury was observed at Desert Research Institute during the summer. That's this bar down here. In general, the summer elemental mercury was lower than the spring elemental mercury. So we see this pattern across sites where we had multiple seasons of data. There it is lower in the summer than in the spring. And when we filtered the data to produce the free tropospheric set, it generally lowered the elemental mercury concentration. And that was especially prominent at NVO2, which is right here. So you can see the difference. I'm sorry, that should be open. That should be unhashed there, but you can see that all the data was here at about all the data is up here at 1.8, and the free tropospheric data is down here at 1.6. The reason for that is there's many geogenic sources in that Nevada region, and so when we filter out for the time periods that are influenced by surface air movement, the elemental mercury concentration goes down. In the model, we also see the highest elemental mercury concentrations at the Lulin site during the spring, so that feature is well represented in the model, and it's primarily due to outflow from Asian sources and probably biomass burning, as Gui Rong mentioned yesterday. We also see a similar seasonal cycle in the model as in the observations, so the summertime elemental mercury is lower than springtime, and that difference between summer and spring was identically matched at Mount Bachelor. 11% lower in the summer than in the spring was seen in both the observations and the model. However, the low values at DRI were not reproduced in the model. The model had elemental mercury concentrations that were 32% higher than the observations. Okay, so let's look at reactive mercury here. Quite a variation between sites and a pretty large offset between the observations and the model. However, in the observations, reactive mercury varied by about 7 times between the sites, and there was also about a factor of 7 variation between sites within the model. Seasonal cycle, reactive mercury was highest in the summer, except for at labs where the summertime meteorology is dominated by tropical convection. And the filtering the data for the free tropospheric data set had a large effect on reactive mercury. It was much higher for the free tropospheric data set, especially in the summertime at Mount Bachelor, DRI, and Storm Peak. In the model, there wasn't much of a seasonal cycle predicted for reactive mercury. The springtime reactive mercury was about the same as the summertime reactive mercury, especially at Mount Bachelor and Storm Peak. And then looking at the absolute magnitude, the modeled reactive mercury was greater than the observed reactive mercury by about a factor of 2.5 overall. Okay, but as I said, the absolute comparison was not really the focus of the paper. What we wanted to look at was, do we see similar relationships between the chemical species in the atmosphere? So this is the summertime data only from the 5 sites. We had summertime data for all the sites. And what we see here in the linear regression slopes plotted as a function of site, both for the observations in black and for the model in red. For the summertime, this is reactive mercury versus elemental mercury. And you can see that the relationship is predominantly negative in the observations and in the model, except with this notable exception here. The model predicts a positive correlation between elemental mercury and reactive mercury, probably because of some pollution outflow contribution, which was not observed. But in general, the observations show a consistent negative relationship between reactive mercury and elemental mercury. For reactive mercury versus ozone in the summertime, we see fairly good comparisons. So the relationship is positive between reactive mercury and ozone, both in the observations and in the model, although at labs and DRI, the relationship is rather weak, but it still is registers as positive. And the relationship between reactive mercury and water vapor shows that the relationship is generally negative across all sites. So we see a nice comparison there between the observations and the model. So from this, we can conclude that reactive mercury is formed in the free troposphere where water vapor was low and ozone was high from the photooxidation of elemental mercury, resulting in low GEM. And this is not going to make the headlines anywhere. We kind of already know this, but this is the first attempt to compare across sites and integrate with the model, and this is a consistent story that we see. Now, this is the summer. In the spring, the story is not so clear. Okay, here we still see some negative relationships at Mount Bachelor and at Storm Peak. The model predicts a much stronger negative relationship than what was actually observed. But at DRI, the relationship observed was actually positive. And so we don't see as good of a comparison between the model and the observations. For ozone and reactive mercury, we see a very weak relationship in the observations, whereas what was predicted in the model was much stronger. And at Storm Peak, is actually observed a negative relationship, whereas the model predicted a positive relationship. Water vapor, similar story. The model predicts strong negative relationships, but the observations were either more weakly negative or, in the case of Mount Bachelor, actually positive relationship between reactive mercury and water vapor. So not typically what you would expect if you're assuming that the reactive mercury is being formed under dry air. That's not always the case. So we have some ideas that would need further testing. There could be transport of reactive mercury from non-free tropospheric regions. There could be unknown oxidation mechanisms that were not included in the model. And there could be chemical forms of reactive mercury that were poorly detected by the analytical system. Okay, we looked up close at an event. And this was an interesting event in high GOM, well, high reactive mercury, but largely dominated by GOM. It was observed sequentially at 3 sites. So from west to east, it was observed, you can see in the black line down here is the reactive mercury. It peaks on June 21st of 2007 at Mount Bachelor and at about 250 picograms per cubic meter, the 12-hour average. And on between the 23rd and the 24th, it was observed at the Desert Research Institute at about 250 picograms per cubic meter. And a little later on the 24th, at a much lower level, it was observed at in northern Nevada, a little bit further to the east. So we can just point out some other features of this. The elemental mercury during this time period showed a decrease as the reactive mercury increased. You can see that the GEM, the black line here, is going down. There's a lot of sawtooth pattern in at the Nevada sites. This is due to the diurnal cycle. You don't see that as much as at Mount Bachelor. You also see lower water vapor and higher ozone generally during these time periods. And the model comparison is shown. What I wanted to focus on is the reactive mercury to GEM ratio during these events. The observed is shown here in the first number. This is in units of picograms of reactive mercury per nanograms of elemental mercury. And we see that close to negative 1,000, which indicates a quantitative conversion of elemental mercury to reactive mercury that was seen in the observations, and a pretty good agreement with what was seen in the standard model. At DRI, which saw a perfect agreement, really, between the two slopes, and at NVO2, not quite as perfect, but the trend is interesting because as this air mass came from the west and was subsiding, it showed the highest negative slopes at Mount Bachelor and the second highest at Desert Research Institute and the third highest at NVO2, and the model was able to capture that trend even if the magnitudes aren't exactly the same. Just looking at where the airflow is coming from, these are gridded frequency distributions of high split back trajectories going 5 days back in time, initialized at Mount Bachelor during the peak of the event, Desert Research Institute during the peak of the event, and NVO2. You can see that the flow is generally from the west. It branches off with a couple different patterns depending on which site it's arriving at. But what's interesting, and as I show the lower plots here, this is where we actually look at the different altitudes of the air mass as predicted by high split. And high split will calculate the boundary layer height. So in each cell, I look at the fraction of trajectory endpoints that are either above or below the modeled boundary layer height. And so the squares, the grid cells shown in brown, are those which have greater than 10% of their trajectory endpoints below the boundary layer height. So in other words, a significant contribution from the boundary layer. And at Mount Bachelor, you can see that this is this airstream that goes off to the north, coming from the marine boundary layer. But there is an airstream that's coming from the south and the west that has a significant probability, greater than 50% probability in that square right there, that represents the descending air from the free troposphere. And each of the sites show at least one grid cell that is in the red here, which represents a location probability of greater than 50%, indicating a significant portion of the airflow coming from the free troposphere. But again, the overall airflow pattern is complex because you have a mixture of subsiding free tropospheric air and lower altitude boundary layer air. Okay, so the last portion of the talk here, I want to compare the different outputs from the model using the different oxidation chemistries. So the standard model uses the bromine oxidation scheme, and the alternative to that is using the ozone oxidation scheme. Now, the mercury community generally accepts that bromine is the preferred global oxidant for elemental mercury, and OH and O3 have had certain issues raised about their likelihood of being important in the global oxidation for mercury. But nonetheless, we wanted to see what kind of range could we get by running different oxidation schemes, and how would that either improve or make worse the comparison between the model and the observations. So I'm focusing on two of the sites here, Mount Bachelor and Desert Research Institute. This is where we have the most data and the highest concentrations of reactive mercury that were observed. And so this is a time series in 2007 from April to July, and the observations are shown in black. You can see there's some spikes here. This one in June over here was one that I showed you recently a close-up of. And then we have the elemental mercury. You can see the seasonal pattern decreasing into the summer. The observations shown in black, standard models shown in the solid red, and the OH-O3 model shown in the dotted red. Let's look at the DRI data. You can see observations of reactive mercury shown in black. Here, the observations are actually higher than the model. Kind of funny. Here, the observations are lower than the model. both models. GEM, the model tends to be higher than the observations at both locations, although when you use the O3OH chemistry, you get a closer agreement. So, okay, yeah, I'll just wrap it up here. So when you look at a scatter plot of this time series data that I just showed you, you can see that by varying the model chemistry for the Mount Bachelor data, it doesn't give you a radically different result. Okay, you see R-squareds around 0.1 to 0.15, slopes between 0.3 and 0.5, not a whole lot of difference. However, when you look at the DRI data, you see a very different picture. You see a significant correlation using the OHO3 chemistry, whereas you see no correlation using the bromine chemistry. And so what we did with this then was to compare the reactive mercury to elemental mercury ratio that was observed versus the reactive mercury to elemental mercury ratio that was modeled at each site for each month. So in other words, the monthly mean of the observed ratio versus the monthly mean of the modeled ratio. And this is the pattern that you get for all the sites and all the months using the standard model with the bromine chemistry. And there's not a lot of pattern here, especially the DRI data. There's really no relationship. If you squint, you might be able to group the sites. The red is Mount Bachelor. It sort of groups with the Storm Peak data, heading off in this more of a linear relationship, whereas the desert sites, DRI and NVO2, are more of a vertical, nonlinear relationship. Okay, so now let's look at the pattern when we use the OHO3 chemistry, and a relationship emerges. We now see all sites grouping along a somewhat consistent path. We see the greatest shift for the desert sites, where the relationship used to be basically straight up and down. Now it is more of a significant linear relationship. Okay, so anyway, I'll just wrap up here with the conclusions. We see that we can determine that photooxidation of GEM in the free troposphere is important, but it's mostly important in the summer over the spring. We saw equivalent variability across the sites in the model and the observations. The absolute comparison showed an offset both in RM and GEM, but during an event, the RM to GEM ratio, the trend there was reproduced in both the observation and the model. We see that when we go to the OHO3 oxidation scheme, we see a closer agreement with the observations at DRI compared with the bromine oxidation scheme. Varying the oxidation scheme at MBO did not change the comparisons quite as much. This suggests that the OH as an oxidant via the mercury bromide plus OH pathway, which has been proposed by Dibble, could be more important in the summer at the desert sites as opposed to the mountaintop sites. So with that, I'll take any questions. Thank you very much.
We don't really have time for a question, but does anybody have like something burning that they? No? Okay. Okay, so let's just move on.